The next is set of tests which we can perform in this session are comparison of the populations. In the earlier session, we have primarily looked at the hypothesis test involving single population. Single population, we tried comparing the means, variances, proportions, etc. Now, the same scenario, we will extend it for the comparisons between the two different populations. So, comparison of the means between two different populations, variance known, variance unknown, comparison of the variances between two different populations, comparison of the proportions between two different populations in a binomial parameter, in a binomial scenario, and even the comparison of the Poisson means between the two sets of data. All these things we can do between two different populations and make a similar kind of conclusions. So in all these, the process remains the same. In these kind of tests, the null hypothesis is again the uniformity or the equality or no difference between the parameters of the two different populations. So that is what is the null hypothesis we'll start with. It's equal to something, whereas the alternate goes with the not equal to, or in some cases we have seen depending on a one tail or a two tail test, it will go as less than or greater than kind of relationships. So we'll try to execute those kind of things by taking the examples again. Alright, so with that background, let's get started. Now again, differences between the means of the two different populations. So hypothesis test comparing the means of two different populations. Again, normally distributed, variance known, variance unknown. Two cases. Depending on the way, if the variance is known, we will use the standard normal distribution. If the variances are unknown, we'll use the t distribution. Even that logic remains the same, right? Whereas if we see the test statistic is slightly different. Whatever is the sample difference, if we see here, okay, the hypothesis, the null hypothesis for us in this case is the difference is equal to hypothesized value. So again an equality. Difference in the averages or the means is equal to some hypothesized value. The most common scenario is the difference is equal to 0, which means there is an equality between the two population means. That's the most common kind of a scenario we'll come across. But sometimes, yeah, this is 2 more than the other one. Even those kind of cases, the average of males is 5 more than the average of the female. Even that can be taken as null hypothesis because there is an equality kind of a principle that can be built into it. So the alternate again is difference not equal to. In case of a two-tailed test, we'll say difference not equal to hypothesized value, or in case of one-tailed test, we'll go with either difference less than or greater than the hypothesized value. Fair enough. So this is the scenario which we are focusing on. So that's the reason the test statistic for us comes out as, okay, instead of taking the value, the sample mean, we take the difference between the sample means, difference, the hypothesized difference divided by the standard error. When the earlier only one was there, we are taking it as sigma by root n. Now, because there are two different populations, the combined thing is taken as sigma 1 squared by n1 plus sigma 2 squared by n2 and the square root of it. Probably when only one was there, it was as good as square root of sigma squared by n. That is what has come out as sigma by root n. Now that is where when two of them are there, we are adding up at the sigma squared by n layer, and from there we are trying to find out the test statistic. And the same logic, if the population variances are not known, the numerator still remains the same. Whereas in case of the denominator, instead of sigma 1 squared by n1 plus sigma 2 squared by n2, what we do is we come out with what is called as a pooled variance. The pooled variance is what we call as SP, the pooled variance. And the pooled variance actually is computed by this kind of a formula. The sample size, the first one sample size minus 1 into the variance of the first one, it's like a weighted average variance. So n minus 1 is the total. So it's like a squared sum of the squares of the errors, sum of the squares from the mean. n1 minus 1 s1 squared plus n2 minus 1 s2 squared, as if I have pooled the entire data. n1 minus 1 s1 squared plus n2 minus 1 s2 squared divided by n1 plus n2 minus 2. That is what will give me the combined pooled variance. Using that pooled variance, we will find out the value of the t statistic and test it with n1 plus n2 minus 2 degrees of freedom, and based on that we'll make our conclusion whether these two populations are equal in the mean or they are significantly different in their means. All right, so once we look at the example, we'll get the clarity here. Just go through this example. So there is a comparison between two sets of data on the miles per gallon. So I want to check whether there is equality in the miles per gallon for this versus this. So that's where I am saying the difference is equal to 0. All right, and in this example there is no population standard deviation or the variance given. It's only the raw data that is given, which means the standard deviation of both the populations I have to compute from the sample itself, which means I cannot use the standard normal distribution in this example. I have to resort to the t distribution itself, right? So we'll go ahead by taking the data first and then looking at what all values I require. So as a part of the t-test, if we see now, okay, n1 plus n2 minus 1 degrees of minus 2 degrees of freedom. So we know that n1 is 8, n2 is 8. So I need x1 bar, x2 bar, which are nothing but the sample means. I need the pooled variance, which can come from the individual variances. So once we compute all those things, we can execute our test and then do the comparison, because that entire thing is following a t distribution with n1 plus n2 minus 2 degrees of freedom. All right, so let's get started with the data. So for the type 1, the data is, I'm just copying down the data. Okay, that's the first set. Going to second set. So these are the two sets of data that we are more interested in. Okay, from this at least some of the things that we can directly take up, the sample sizes. N1 is 8, N2 is also 8. So probably degrees of freedom, I can take it as N1 plus N2 minus 2, N1 plus N2 minus 2, which is 14. All right, and I need sample mean 1, which is x1 bar, and I also need sample mean 2, which is the x2 bar. Okay, so I'm taking the average of the first sample, which results in 28.3. I'll take the average of the second sample, which results in 30.75. Okay, I also require the variances of both. I could have computed the standard deviation, but anyhow, across we require the variance itself. Even we'll find out the pooled variance itself. So I'll take the variance of the first sample, I'll take the variance of the second sample. All right, probably you know the mechanism of computing the variance, so that's where I'm directly taking the values. I'm taking the variance of the second sample. Okay, this is the variance of the second. So from here I can even find out the pooled variance, which is we have that formula n1 minus 1 into s1 squared, n1 minus 1 into s1 squared, which is the variance of the first one, plus n2 minus 1 into s2 squared. This entire thing divided by n1 plus n2 minus 2. So the pooled variance can be taken up as 5.96. Now if we see here, sp squared is 5.16, going with this formula. So based on this, I can find out the pooled standard deviation, which is the square root of the above, which works out to 2.44. Fair enough. Now I can apply the test statistic, because the question is check for 0, whereas the alternate check is for greater than 0, which means the alternate hypothesis is a one-tailed kind of a test. So probably in this, my null hypothesis comes out to be less than or equal to 0. The null hypothesis works out that the mean is less than or equal to 0 and the alternate comes out to greater than 0. Right? So the hypothesized difference is 0. Sample differences we know. So based on that, let's go ahead computing the test statistic. So the test statistic for us is the sample mean differences. Either way I should be able to do, no issues. The difference in the sample means minus the hypothesized difference, which is 0, divided by the pooled standard deviation into square root of 1 by n1 plus 1 by n2. So 1 by n1 plus 1 by n2. This is what is giving me my test statistic, minus 2.00. Minus 2.00 is the test statistic. Now what I can very well do is use this test statistic to compare with the one sample t-test. with the critical value associated with the one sample t-test, because this value follows uh, uh, a t-distribution. This entire test statistic follows a t-distribution with n1 plus n2 minus 2 degrees of freedom. So I can very well find out the critical value by looking up into the t table. So because the question is being given as mu a minus mu c greater than 0, so I have to take the difference the other way. Mu a minus mu c, not mu c minus mu a. Doesn't matter. It's only the sign change that comes out. So here I take the first one, and here I take the second. So the whatever was negative earlier calculation, now it comes positive. Nothing else will change. So my test statistic is 2. And now what you can look out for is the critical value corresponding to 14 degrees of freedom and 5% in the tail. What is the area corresponding to 5% in the tail? This is the area corresponding to 5% in the tail. So corresponding to 14 and 5% in the tail, the value comes out to 1.761. So the critical value for us is 1.761. Even if I use this, because I need a one tail test, I take the probability as 10%. So 1.761 is the critical value, and what it is coming out to us is the actual difference based on our sample is outside the limits of the critical value, which means it is in the rejection region. So I can reject my null hypothesis and make a conclusion that at 5% level of significance, I can very well say that there is a significant difference between the means of the two populations. And it is also saying that the mean of the one population is definitely greater than the mean of the other population. Now let's see, there is a slightly different question that is also asked, right? It is saying H naught is mu a minus mu c equal to 6, and H1 is mu a minus mu c not equal to 6, which means the difference between the two, I'm equating it to 6 versus not equal to 6, which means it's a two-tailed test, and the hypothesized difference is 6. So what all changes that will come? Here, instead of 0, I'll take this as 6. That's one aspect, which has given me that my test statistic is minus 2.9, and the critical value also is taken with respect to two tails. So I'll take this as 5% here. So based on this, this comes out as plus or minus 2.14. What does that mean is the test statistic, if it is outside the plus or minus 2.14, then we say that it is in the critical region and the null hypothesis can be rejected. So even it can be said that the, the the difference is the difference between the two is really not equal to 6. There is it is nowhere equal to 6, but at least it is significant. The difference is significant, but that difference is definitely not equal to 6. So that kind of a conclusion can come out. So depending on what the data is and what kind of test we are performing, and whether it's a one tail or a two tail test, what changes, the test statistic may not change unless the hypothesized value changes, but the critical value will definitely change. based on whether we are going for a one-tail test or a two-tail kind of a test. So the final conclusion is this in this example. All right. So if at all I have to do a comparison of the population means of two different normally distributed populations, we can use this kind of a test. All right. Now, the same scenario, let's say if I have to test for equality of two variances, one variance with a constant, with a hypothesized value, we have used the chi-square test. Whereas if I have to compare two variances, we'll use an F test. The F test statistic is very simple. The variance of the first one divided by the variance of the second one. So the ratio of the variances of two, so we can simply take the ratio of the two, and that ratio will follow a kind of F distribution with n1 minus 1 and n2 minus 1 degrees of freedom. Then another kind of test that we have done in case of one population scenario also is the testing for the proportions, and there we have gone for the normal approximation to the binomial distribution. So the same logic again, if at all I have to test for the differences between the two proportions, I can use the same. Instead of taking the proportion of 1 in the numerator, I am taking the difference between the two proportions from the two different samples, and in the denominator we have the standard deviations itself. So that is what we are typically doing, and that entire thing follows a normal distribution, a standard normal distribution with mean as 0 and variance as 1. The same thing we'll try to do it with our example, testing for the equality of the binomial parameter or the proportions. So I say the hypothesis test for equality of two proportions. In this case, again, look at the example, then we'll try to discuss a little bit more. In 1 year mortality investigation, 25 of the 100 90-year-old males, 20 of 150 90-year-old females started. So probably one proportion for me, P1 or theta 1, whatever we call. P1 is 25 upon 100, which is for the males. P2 is 20 upon 150, which is for the females. All right. What is it saying? Assuming that the number of deaths follow a binomial distribution. So we are talking about a binomial distribution. So we are looking at the comparison of the proportions. So P1 and P2 we know. So based on that, in the denominators we can find out P into 1 minus P by N1. All right. So what is that? I can find out P1 into 1 minus P1 by N1, which is coming out to P1 into 1 minus P1 divided by N1, which is 100. All right, P1 into 1 minus P1 by N1. The same logic I can do for the second, P2 into 1 minus P2 by N2, P2 into 1 minus P2 divided by N2, 150. So I have P1, P2, all these things. All right, so what is my null hypothesis here? The proportions are equal, P1 equal to P2. And alternate is whether there is a difference. So we are talking about not equal. We are not talking about a greater than or a less than relationship here, which means I can go for a two-tailed test. I think by now you should be comfortable in what has to be used in what scenario. So based on that, if I compute the test statistic, what is that? The proportion 1 minus the proportion 2 divided by the square root of, if you see here, square root of p into 1 minus p by n1, p into 1 minus p by n2 kind of stuff. So square root of this plus this. So this is what is our test statistic, which has come out to 2.26, and we are saying that it follows a standard normal distribution with 0, 1. So at 95% confidence level or 5% significance level, we know that the critical value is 1.96. We don't need to check out in the tables. For a two-tailed test, the critical value is 1.96, which means my test statistic is lying in the critical region outside the plus or minus 1.96 layer, which means I will reject the null hypothesis and simply conclude that at 5% level of significance, there is a significant difference in the proportions between the two populations. This is the conclusion that comes out to us. So if at all I have to do a comparison of the proportions of two populations, we will resort to this kind of a test. And finally, in the same lot, we also have hypothesis testing for equality of means of two Poisson distributions. Even the same logic. Look at the same. The means of the two datas, the means of the two populations divided by square root of lambda by n1 plus lambda by n2. That is what is the test statistic that is typically used. The null hypothesis is both the means are equal. The alternate hypothesis is there is a difference between the means. So look at the numbers again. 150 claims from 500. So N1 is 500 and the claimed X1 is 150. So probably lambda 1 is 30%. All right. What about the next? 650 from 4,500 remaining. So N2 is 4,500. X2 is 650. So from here I get lambda 2 is the proportion is 650 divided by 4,500, around 14.4%. All right. Assume that the number of claims made by the individual motorists are Poisson distribution. Significance level is 1%. All right. Whether the claim frequency is same for the drivers. So same means we are going with the null hypothesis is saying lambda 1 equal to lambda 2, lambda 1 equal to lambda 2, and alternate hypothesis is saying lambda 1 not equal to lambda 2. It's a two-tailed test because we have to test not for greater than or less than two-tailed test, and we have already seen that this follows a standard normal distribution. So based on this, I'll compute my test statistic, which is the difference between the lambdas Okay, the difference between the lambdas divided by the square root of lambda 1 lambda by n1 plus lambda by n2. So I'm taking the lambda, which is nothing but lambda by n1 plus lambda by n2. So the test statistic is 6.18, and the critical value for us always, because it's a two-tailed test, the critical value is 1.96. So we are outside the critical value limit. Yeah, in this case, the combined lambda, okay, will not take the independent individual lambdas. Will take a combined lambda. So I'll actually, this is a mistake which I have done. I'll have to find out the combined lambda, which is nothing but the combined x's, all right, combined x's divided by the combined n. I think the same thing I have to do even in case of the proportions earlier. This was a mistake. Just take it as a correction. So the combined lambda is 0.16. All right, so this is what we have to actually do. So in the test statistic, I'll modify it, especially in the denominator. I'll take it as the combined lambda by n1 plus again the combined lambda by n2, not the individual lambdas. I'll take the combined lambda by n1 divided by combined lambda by n2. Yeah, anyhow, it doesn't matter. The test statistic is 8.24, which is way outside the plus or minus 1.96 range, which is where I will be rejecting the null hypothesis and conclude that there is a significant difference in the mean value of both the proportions of both the data. All right. The same logic we should actually use in case of binomial also. In the denominator, I should not take p1 into 1 minus p1 by n1. I'll take a combined p itself. So I'll take combined p, just a correction. So in the combined p, I'll take 45 divided by 250. So this becomes my combined p, 45 in the combined p. I'll take 45 divided by 250.18. So the p into 1 minus p by n1 by n by n1 is coming out to p into 1 minus p divided by n1 is 100. So p into 1 minus p by n2 is coming out as p into 1 minus p divided by n2. These are the two numbers. So while computing the test statistic, I'll not make the mistake now. Instead of these two, I'll have to actually add up these two. So anyhow, they are resulting in 2.35 again outside the limit itself. So there is no change in our decision, at least in this example. But from a correction standpoint, we have to make sure that we don't make this mistake. So if you see in the formulas also, the denominator does contain only theta. It does not contain theta 1 and theta 2. The same is the case in case of Poisson parameters. The denominator contains lambda. It does not contain lambda 1 and lambda 2. Lambda is nothing but a pooled lambda. Pooled lambda. So we have to go with that pooled value, and based on that do our kind of a testing. Alright. So in some scenarios there is a possibility of we being able to compare between two different populations. We may be ending up doing a comparisons on the means, on the variances, or on the proportions. All these kind of comparisons we should be able to do, right? So this is one set of hypothesis testing that we should be comfortable in doing. Then we have a couple of more, right? And there is one more, okay, in terms of the group of data itself, in terms of two different populations itself. If the populations are independent, and I have to find out the difference, the average difference between the two population means we have used the average of the first population minus the average of the second population, and so on, and finally created either a Z distribution or a T distribution. But some cases we may end up with paired data, which means they are actually not the two populations are not independent, but they are typically pairs, especially the scenarios like before and after, right? Especially before and after, which means the two data sets are actually not two independent kind of data sets, but before addition of something and after the addition of something. So especially before and after scenarios are probably the male and female as a pair, a person and his spouse. So they cannot be looked at as two independent sets of data, male and female. Here if I choose a male, the female is not a random here, right? It is a pair associated with that male. Whenever we have a data like that, we call it as a paid sample kind of a data. And especially if I have to check out that whether there is a significant difference before and after kind of scenarios, we use the difference, the sample. We take the differences of the each of the samples separately, not the average of the first population and average of the second, and I don't do the subtraction at that layer. We find the difference at each of the sample layer, and we find the mean difference, compare it with a hypothesized difference, and we take the standard deviation of the differences divided by root n. Let's look at this scenario, right? If the question is about before and after, if the question is more about before and after, let's look at this. So I'm talking about hypothesis on a paired data. So in this paired data, okay, sample data is what I'm first looking at. Let me copy the sample data. Let's say this is the sample data for before, and this is the sample data for after. Okay, this is the sample data for after. What it is saying, so for 5 employees are sent for a training, the time in seconds to carry out the task before the training and after the training. So I want to find out whether there is a significant difference in each of the persons in terms of the effectiveness from the training. So it's a pair. So for that, what we typically do is we at each of the individual layer we will find out the difference. At each of the individual layer before and after, we'll find out the difference. And we'll now find out the mean difference, sample mean difference, which comes out as the average of these numbers. So the sample mean difference is 4.6. I also find sample mean standard deviation, wherein I'll take the standard deviation of these. So that's the level of standard deviation that is existing. And the null hypothesis for us is before and after no difference. So which means the difference at each of the individual layers is 0, whereas the alternate hypothesis is the difference not equal to 0. So if the question is about has the desired effect, so the actually speaking, I want to look at whether there is an improvement. Improvement is the difference should be greater than 0. So probably I want to look at only one tail test, the difference being greater than 0, because after is a scenario where I'm taking in the after case the number should come down, so I'm looking at one tail test, and based on this I'm looking at the test statistic, which is nothing but the sample mean difference minus the hypothesized mean difference, which is 0, divided by the s by root n. So s is 6.1 in this case. S is 6.1 by square root of n is 5. So my test statistic is 1.68, and because we are using a one tail test and a 5% level of significance, because this follows a kind of t distribution with n minus 1 degrees of freedom, I can check out corresponding to the t value and 4 degrees of freedom, 5% level of significance in one tail, which is 2.132. The critical value is 2.132. So all it is saying is my difference is not beyond 2.132. It is much below 2.132, which means I don't have significant evidence to conclude with this just 5 data points. I don't have a significant evidence to conclude that the training has really improved the efficiency level of the participants. Though overall for 4 people there was an increase and only for one person there was a decrease, because the standard deviation is very high, and even the sigma by s by root n is also much higher. Overall the test statistic has resulted in only 1.68, and probably the critical value is 2.1. So greater, if it had come to greater than 1.6, greater than 2.1, then I would have rejected the null. But here I don't have the evidence to reject the null hypothesis. I will go ahead with the null hypothesis also, and I can very well conclude that at 5% significance level, there is no solid evidence to say that the training had really improved the performance of the employees. Alright. So especially when you are working with two different populations, these are the various scenarios you may come across. comparing the means of the two populations when the variance is known versus when it is not known, comparing the variances of two populations, comparing the proportions of the two populations, comparing the means of two Poisson distributed populations, and finally comparing the means of the paid kind of data, comparing the means in case of paid kind of a data. So we have to really understand what is the typical scenario I need to test, and based on that I have to choose the appropriate test statistic and the distribution, and identify the critical value correctly, based on which I should take whether my accept or reject decision needs to be gone with. And now we have one more scenario where we may have to do the hypothesis testing on categorical data. Till now the entire testing which we have done is on quantitative or a scale kind of a data. Now we will be focusing on a couple of tests which focus on the categorical kind of a data, or nominal or ordinal kind of a data. So tabulations of the frequencies and all. So that is one more area which we would be focusing on in terms of the hypothesis testing process. So you may have to do some kind of a practice on whether the scenario is more to do with one population equating it to some hypothesized values, or comparison of the parameters across two different populations. All right.